16.2, we'll be looking at set operations and compound inequalities. Before we get started on examples, we're going to start looking at some vocabulary for this section. So the first thing is the intersection of sets. So when you see this notation, that's read the intersection of A and B. So the intersection of A and B is the set of any values x such that x is an element of A and x is an element of B. So in other words, the intersection is the set of everything that they have in common. Okay, so in order for some value x to be in the set of the intersection, it has to be in A and it has to be in B. Okay, so we'll look at example 1. List the elements in each set. So A is the intersection of A and B. If A is the set of numbers 3, 4, 5, 6, and B is the set of numbers 5, 6, and 7. So remember that the intersection means it's what they both have in common. It has to be in A and in B. So we're going to look at both sets of numbers and see what they have in common. So they both have a 5 and they both have a 6. So that means that the intersection of A and B is equal to the set of numbers 5 and 6. Example B is asking us for the intersection of N and O. So N and O, this table comes from the top of page 1151, the very first thing on section 16.2. And the paragraph under tells us that N is going to represent the underactive thyroid and O represents the overactive thyroid. So these are my values in each, and we're looking for the intersection. We're looking for something they have in common. So we have intolerance of cold, intolerance of heat, dry hands, moist hands, sleepiness, insomnia. Those are all opposites. And then this last one, goiter, is what they have in common. So since they're using G to represent that, then the intersection is just going to be the set of G. That's the only value that they have in common. Okay, in the next example, we'll be solving compound inequalities. So the steps for solving a compound inequality with AND, so that's going to be with the intersection. You're going to see the word AND in the question. Step 1 is to solve each inequality separately. And then step 2 is the solution set is going to be all the values or numbers that satisfy both of the inequalities in step 1. So it's important to note that these steps are for solving it when it has the word AND. So we'll look at some examples so you can see more specifically what that means. Okay, so on example 2, we're going to solve the inequality x is less than 10 and x is greater than 2. So step 1 was to find each one separately, and then it's going to be everything that they both have in common. So we're looking for numbers that are less than 10 and also greater than 2. Alright, so numbers that are less than 10 are like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so this is how I would graph the number line. So we'll go all the way up to like 9, 9.1, 9.5, 9.9, but never exactly 10. And then x is greater than 2. We're going to have 2 on my number line, and everything greater than, so 2 is not included, but it starts right after 2, and everything that's greater than that. So now what overlaps? Well, we overlap everything greater than 2 and less than 10. So my interval notation would be just like my number line says, from 2 to 10. That's where I have my two colors. That's where they overlap. That's where they have in common. And then my graph would just show from 2 to 10. So if I was graphing it, I would just graph like this and just shade that middle portion. On example B, I have x plus 3 is less than or equal to 1, and x minus 4 is greater than or equal to negative 12. So the first thing I'm going to do, step 1, is to solve each one separately. So I'm trying to get x by itself. So subtracting 3 gives me x is less than or equal to negative 2. And then solving the next one, I'll add 4. So x is greater than or equal to negative 8. Okay, so if I go ahead and put negative 8 and negative 2 on a number line, then my first inequality is x is less than or equal to negative 2. So less than, I'll shade this way. And then my second inequality is x is greater than or equal to negative 8. So negative 8 and everything greater than is this way. So since it's an AND question, we're looking at where they overlap, what they have in common. So they're going to have everything in common from negative 8 to negative 2. And then the number line would be shaded between those two and including them. Make sure you use brackets because of the equal to sign and the inequality. For example 3, we have 2x is greater than or equal to x minus 1, and 3x is greater than or equal to 3 plus 2x. So remember, step 1 is to solve each inequality separately. So I'm going to subtract 1x from both sides. So 2x minus 1x is just 1x is greater than or equal to negative 1. And then on the next one, I'll subtract 2x from both sides. So 3x minus 2x is 1x is greater than or equal to 3. So I'm going to graph both of those. So I'll have negative 1 and 3 on my number line. So the first one, x is greater than or equal to negative 1. Shade everything greater. Then the second inequality, x is greater than or equal to 3. So again, it's an AND question, so I want to know what's in both inequalities. So what they both have in common is this part of the graph, which is greater than or equal to 3. So my interval notation is going to be 3 to infinity, because the positive infinity, the arrow is shaded. And then my number line would have everything shaded from 3 onto infinity. On example 4a, we're trying to find the compound inequality of x is less than 5 and x is greater than 5. So what numbers are less than 5 and also greater than 5? None. So since a number can't be less than 5 and greater than 5, there's no answers that fit that solution, so this is going to be the empty set. On example B, we have x plus 2 is greater than 3 and 2x plus 1 is less than negative 3. So we're going to solve each one. So I'll subtract 2 from both sides. It's give me x is greater than 1. And subtracting 1 from both sides gives me 2x is less than negative 4. Dividing by 2, x is less than negative 2. Alright, so graphing these, if I graph x is greater than 1 first, and then x is less than negative 2. So remember, it's an AND question. I want something that fits both. Well, looking at the graph, you can see that they don't overlap ever. If something's greater than 1, it's never going to be less than negative 2 also. So again, this is going to be the empty set. The second type of problems that we're going to be working on is a union of sets. So we've been working on the intersection, which is what they both have in common, A and B. The union of sets is the set of values of x such that x is an element of A or an element of B. So rather than it being what they have in common, it's going to be everything combined. So if it's in A or if it's in B, it's going to be part of the union. You're combining them together. So example 5A is asking us to find the union of A and B if A is the set of numbers 3, 4, 5, and 6, and B is the set of numbers 5, 6, and 7. So remember, the union means if it's in A or B, it counts in the union. So 3 is in A, 4 is in A, 5 is in A and in B. We're still only going to write it once. 6 is in A and B. We write it once. And then 7 is in B. So it's the combination of the two together. Just make sure you don't repeat numbers. If it's in both, you still only write it one. So that's equal to the union of A and B. So for example B, we're again looking at N and O from the table at the beginning of the section. So the union for this one would be the set that contains S, D, C, G is only going to be written once, I, M, and H. Okay, so solving a compound inequality with OR. So when we're talking about unions, the word OR is the one that is related to finding the union of two sets. So step 1 is the same, solve each inequality individually, and then step 2, the solution is going to be all of the numbers that satisfy one or both inequalities from step 1. So it doesn't have to satisfy both, it can be in one or the other, or both. Example 6 on page 1154. We have x plus 2 is greater than 3, or 2x plus 1 is less than negative 3. So again, step 1 says to solve each one individually. So I'm going to solve for x, subtract 2 from both sides. So that gives me x is greater than 1, or subtract 1 from both sides. X is less than negative 2. So I have my number line. So the first one is x is greater than 1. And then I'm also graphing x is less than negative 2. So since there's no overlap, this is what my graph would look like. And then my interval notation, remember your interval notation follows your graph. So since I have the arrow shaded, it's going to be negative infinity to negative 2, union 1, and then this is positive infinity. So your interval notation is going to be all of that. Okay, so example B, x minus 1 is greater than 2, or 3x plus 5 is less than 2x plus 6. So we'll solve each one individually. So x is greater than 3, or, in this case I'm going to get my x's to one side. Subtract 5 from both sides. So x is greater than 3, or x is less than 1. So 1, 2, 3. So greater than 3 is here. Less than 1 is here. So if we were looking for the intersection, it would be no solution, or the empty set, because there's no place where they intersect or overlap. Since we're looking for the union, it's just a combination. This is what my graph would look like. And then my interval notation would be negative infinity, because I shaded the arrow, to 1, union 3 to positive infinity, because the other arrow is also shaded. Example 7, a is 2x plus 1 is less than or equal to 9, or 2x plus 3 is less than or equal to 5. So we'll solve each one separately. So we get x is less than or equal to 4 for the first one. And x is less than or equal to 1 for the second. So I have x is less than or equal to 4, or x is less than or equal to 1. So draw your number line. 1, 2, 3, 4. Alright, so the first one, x is less than or equal to 4, less than or equal, I have a brackets, and it's going to be everything less than that. Then x is less than or equal to 1. So that one overlaps it. So remember, we're looking for the union, the combination of all of it, not the intersection. So we're not looking just for the overlap, we're looking for anything at all that's shaded. So in this case, my solution is going to be anything that's shaded. So from 4 on to negative infinity. That's my solution. So my interval notation would be negative infinity to 4. In example B, we have 3x minus 4 is greater than 2, or negative 2x plus 5 is less than 3. So again, we'll solve each one separately. So we get x is greater than 2, or okay, now in this case, remember that when you multiply or divide both sides by a negative, you have to flip your inequality symbol. So it's very important that you remember to switch that symbol because you're dividing both sides by a negative. And then negative 2 divided by negative 2 is 1. So I have x is greater than 2, or x is greater than 1. Alright, so x is greater than 2, and x is greater than 1. So I'm looking for the union, which is both of them combined. So anything at all that's shaded. So that would be everything from 1 on has a shaded region. So then my interval notation is going to be 1 to infinity. Example 8, 3x minus 2 is less than or equal to 13, or x plus 5 is less than or equal to 7. So solve each one for x. So for the first one we get, x is less than or equal to 5, or x is greater than or equal to 2. Alright, so the first one, x is less than or equal to 5. It's going to be this. X is greater than or equal to 2. Alright, so notice that the whole entire number line is shaded. So if I was graphing my solution, I would just shade the whole number line. Okay? And then, so my interval notation would include everything from negative infinity to positive infinity. In example 9, we're looking at the table, and it says we're looking for the set of films with admissions greater than 130 million and gross income less than 800 million. So here's my admissions. And here's my gross income. So we're looking for admissions greater than 130 million. So this one, this one, this one, this one, this one. So that includes all of them. And then the gross income is less than 800,000. I mean, sorry, 800 million. And that's none of them. So if we're looking for things that satisfy both, this is going to be the empty set, because we have things that satisfy A but not G. It has to satisfy both. So the word and means it has to fit both categories.